今天我要讨论 Chapter 9。Chapter 9主要讲的叫 Center of Mass 跟 Momentum。这都是极为重要的观念。先要定义 Center of Mass。在这种情形之下，又是有两个不同的定义，一个是几何的，一个是代数的，然后你可以证明它两个是一样的。我们今天采取代数的。代数假如有很多个 particles， 它的 mass 是 mi。它的 coordinate 是 ri， 在任何给一个 coordinate system 就有很多 ri mi， 于是把这个 mi ri sum 起来，这个被 total mass 除一除，这就叫做 center of mass 的 coordinate。比如说是你有3个 particles， 那就得出来一个 center of mass。这个定义是很简单的假如你只是2个 particle 在1 dimension 的时候，你当然晓得，比如说一个 particle 重，一个 particle 轻，这个你除一下子的话，比如是2个 particle 的话，在1 dimension， 那你就得出来 m1 x1 加上 m2 x2 被 m1 加 m2， 这就等于这 center of mass x center of mass。比如说这 m1 跟 m2 是2:1，那就是比如说这是1，这个的 m2 是2，那么这个 m1 跟 m2 你很显然，因为这个2它这个 weight 比较大，所以你在1/3的地方，这个 center of mass 在这儿。这个我想是直觉的感觉是很简单的。那么这个呢，就是一个 more general 的 definition。有人在上面第一个这个 theorem， the all center of mass so defined is independent of the choice of coordinate system。 因为你这样子一个 algebraic define 出来一个 center of mass， 好了，你比如说有3个 particle，那么你在这 define 出来一个 center of mass， 我利用了一个 coordinate system， 我那换一个 coordinate system 是不是还是这同一个 center of mass 呢？这个 theorem 说是 yes， 可是这需要一个 proof。这个书上在这点上它就是讲的很模糊，在这个书我现在发现它的目的呢是要希望大家容易了解，可是希望大家容易了解以后，它有一些这个比较敏感的地方，它就带过去了。这个 proof 呢其实是很简单的，你取 coordinate 的时候，假如你取了一个 coordinate， 我现在另外一个取 coordinate 是一个 displacement。Change of axis by displacement。 by displacement 就是你把那 axis 平行的动，可是换一个 origin。所以假如你把 coordinate axis 平行动，换了一个 axis， 那么我们问这个后来的 RI 是什么？我叫做 RI prime。那当然 RI prime 就等于原来的 RI 加上那个 displacement， 所以 RI prime 就等于 RI 加上一个固定的 displacement， 这固定的 displacement 就是这两个 coordinate axis， 这 coordinate axis 从这一个走到这个里。假如这个是假如我看这个是这是 R， 这是原来的 x y， 这是 x prime y prime。那么这个 displacement， 那很显然。我看看 R prime 那倒过来了，这是，sorry， 本来都是对的，就是这是，假如一点在这儿。这个是 R， 这是 R prime， 那很显然 R prime 等于 R 加 D， 所以这是 XY， 我的同行，这是 XY， 这是 X prime Y prime， 这是这 displacement， 这个是 R， 这是 R prime。那你看，很显然 R prime 是等于 R 加上 D， 而这个 D 呢是不与 R 没关系的，这个 D 是 displacement of the coordinate origin， 所以你是第几个 particle 没关系。那你把这提到这里的句呢，你就得出来 summation mi Ri prime by definition 是等于 summation mi Ri， 所以这就等于 summation mi Ri 加上 D， 这个 obviously 等于 summation mi Ri 加上这个 D 是 independent of I， 所以就等于 summation mi D。所以 R prime center of mass by definition 是 summation of M 来除这个 summation M I R I prime， 这是新的 center of mass 的定义。这个你把这算一下的话，你把这个，所以就等于 summation M I R I 被 summation of M 除。加上这 summation M 跟 D 消掉了，加上 D， 所以就等于 R center of mass 加上 D。所以换句话说，这个新的 center of mass 的 coordinate 是等于原来的 center of mass coordinate 加上 D， 那就正是跟这图一样。所以这代表说是在 center of mass 你的两个 definition 在一个地方。刚才这是 proof 的第一部分，第二部分是我不动了，我把 origin 不动，把转一转，把这个 coordinate x 这 coordinate x 转一下以后，问是不是这 definition 还是一样？这个呢写起来比较复杂一点，讲起来其实很简单。因为什么缘故？因为这个 definition of center of mass 转了一个 coordinate， 我叫这个 Ri prime， 转的 coordinate 跟原来的 coordinate 是一个 linear transformation， 就是原来 Ri 每一个 R 就有 x y z， 后来的 x prime y prime z prime 是一个 linear combination of x y z。你如果不相信这个，你想想，假如是两个 dimension， 一个 x 一个 y， 你转一下的话呢，那个 x prime y prime 就是一个 linear combination of 原来的那个。而这个 linear combination 不 depend on 你是哪个 i， 你是哪一个 i， 每一个 point 从 r 变成 r prime 这个 linear combination 都是一样的。那所以你如果把这个方程式拿来的话，这右边这个所有的 r i prime r1 r2 r3 都是用同一个 linear combination 把那三个加起来的。那所以左边也是同一个 linear combination。我刚才讲的大家都懂了没有？你可以把它写成 algebraic form， 不是的意思就是我刚才讲的。换一句话说，一个 rotation of coordinate system 就是一个 linear combination of 原来的 coordinate system， 而这个 linear combination 的 coefficient 一共有9个 coefficient。为什么有9个呢？因为你 x prime 只要是个 x y z 的 linear combination， 所以有3个 coefficient。 y prime 也是3个 term， z prime 也是3个 term， 所以是个3乘3的，这是叫做一个 matrix。 那么这个 transformation 就是一个 matrix 乘到原来的那个 x y z， 而这个重要的点是这个 matrix 这9个数目，这9个 coefficient 与你是哪一个 particle 没关系，大家都是一个 transformation。 所以一个 rotation 是 represented algebraically by 一个3×3的 matrix。 大家知道不知道这个 matrix 有个特别性质叫什么名字？这个 matrix 叫做一个 orthogonal matrix。 为什么是 orthogonal 的？这 orthogonal 的意思就是说，原来假如你是个 orthogonal 的 coordinate， 用了这个9个 coordinate， 你后来出来这个还是一个 orthogonal 的 system， 所以这叫做一个 orthogonal 的 matrix。 不是随便写9个都可以，你随便写9个，你们试一下子，你做2×2的2个dimension也有假如我们来一次2个dimension的。两个dimension的这是 x， 这是 y， 那这 x prime 就要等于 cosine theta， 你这转了以后就变成这样。假如这是个 theta， 就变成 cosine theta x 加上 sin theta y， 而 y prime 是等于 minus sin theta x 加上 cosine theta y。 你仔细想想，而你看这个 cosine theta sin theta 这4个数目是一个 2×2 的 matrix， 这个 matrix 叫做 orthogonal。 那么这3个 dimension 就是个 3×3， n dimension 就是 n×n。 可是你看这4个数目它彼此关联起来的，不能随便乱动的。那么同样那9个数目也不能随便乱动，那个 mathematically 叫做它 form 一个 orthogonal matrix。不管怎么样，对我们重要的，对我们现在考虑的重要的呢，就是说你把这个我刚才那张纸，你把这个 Ri 那 Ri 的3个 component x y z 用一个那3×3的东西把它 combine 起来，就变成 Ri prime。那这样你这左面当然也就变成用同样的 combination， 因为都是 linear 的，所以这就证明了刚才讲的 statement， 是说 the R center of mass as so defined is independent of the choice of coordinate system。 我们刚才所证明的是 independent of a rotation of the coordinate system。 那么既然对一个 translation 也 independent， 一个 rotation 也 independent， 那你从一个 coordinate 到另外一个 coordinate 永远是你 rotate 一下，然后再 displace 一下就可以。 是 QED 了。所以第二 rotation， all linear， 这个 key word 就是 all linear， 所以这就 QED 了。刚才讲的有问题没有？这两个是，第一个是需要证明，这个其实是最重要的。通常他的随随便便就不讲，需要证明。第二个会不会证明？这是很简单，你想了以后就其实这需要证明跟 rotation 跟 translation 是 invariant 的，这都是非常简单的事情。OK， 所以这是我们第一个定理有了。然后我要讲第二个定理。Consider two groups of particles.我第一个 group of particle 我叫做 Mi， 它的 coordinate 叫 Ri。第二个 group of particle 我叫做 Mj， 大 M， 它的 position 我叫做 Sj。所以你比如说这有3个 particle 在第一个 group， 然后有4个 particle 在第二个 group。那么这第一个 group 这个 particle 呢，它就有一个 center of mass， 比如说在这。这第二个 group 的 particle 呢，它也有它的 center of mass， 在这儿。画圆圈的就代表 center of mass。所以有2个 group， 每一个 group 自己有一个center of mass theorem. Consider two groups of particles. The center of mass of the total system is exactly the center of mass of two particles. One with mass sum of Ri， 就是第一个 group 的 total mass at the center of mass of these particles. The other with mass summation Mj 是另外那 group at the center of mass of these particles. 就是点点的那个，它们有个 center of mass， 你就 imagine 把那些 mass all concentrate at that point, and then for the second group you concentrate all those second groups of mass at the center of mass of the second group here. The theorem says the center of mass of the total system is exactly the center of mass of only now two particles, one在这一点，one在这一点。Proof。这个 R of 整个的 center of mass， 我们把它写成这样 ，by definition 是等于上面是 summation， 所以你就写成 summation MRI 加上 summation MJ RJ， 底下是 summation of MI 加上 summation of MJ。对不对呢？这 that's the original definition。可是这等于，我现在先把 summation mi ri divide by summation m， 这个是 center of mass of the first group of particles， 把这个人乘上 sum of m， 我现在就是加上 summation mj sj divided by summation 大 M， 再乘上 summation 大 M divided by sum of m 加上 sum of 大 M， 这 algebraically is obvious because this cancel. But what is this? This is total mass at one point times the center of mass of the first group. This is the total mass of the second group times the center of mass of the second group. 把这两个加起来对 total mass 除，这就是后来所讲的，所以 QED。Everybody happy? Okay, now we are going to discuss Newton's equation. Newton's equation is applied to many particles. Similar angle particles. So MI double dot是等于的 total external force on the ith particle. We write that as this. If there are five forces acting on point I, we make the vector sum of these five forces and we write that as U F. 加上 internal forces is summation of F This notation tells you the force on particle I exerted by particle J. 这个 J 箭头 I 的 definition 就是刚才讲这个。OK， 现在我把这个东西 sum， so I'm going to sum this. Sum over I. First you get the second you get the sum of this. So it's a sum of I not equal to J of F I J. But by Newton's third law we know F I J is equal to minus F J I. The force suffered by particle I exerted by particle J is equal and opposite to the force exerted on particle J by particle I. So in here we always have two terms, Fi arrow J and Fj arrow I, and the sum of the two is 0. So therefore this term is 0. So we have a grand theorem, summation MIRI double dot is equal to sum of, in other words, total external force. So if we have a group of particles, if you take the total force on it, you get this very simple equation. It's a trivial statement actually. Now, MIRI definition. MII dot, mass times velocity, is called momentum. The book always calls it linear momentum. Actually, in usual practice, one just calls it momentum. The book calls it linear momentum because later on we're going to study angular momentum. But first, let's stick to linear momentum. In any case, in usual physics language, momentum is equal to linear momentum. 动量。The concept that there's a linear momentum was due to Galileo, and it was Galileo who realized that if a particle does not suffer any external forces, its momentum, its linear momentum, or its momentum remains constant. The reason that was such a difficult thing to realize is because there's usually friction. And so it was thought that if something is not acted on, it would still slow down. Galileo recognized that is due to some external thing. So if you have a very heavy body, it's the influence of friction on it is very little. Then its momentum is constant if it's not acted on by another force. So this is called momentum, and it's usually called Pi. And 这前面的 statement 就变成 sum of Pi ddt 等于 total external force. If a system is not acted by external force, then the momentum is conserved. If a system is isolated, it's not acted on by, it has all kinds of internal forces, but not acted on by any external force, then according to what we just said, its momentum derivative is zero, so its momentum is conserved. So the conservation of momentum is the most important theorem in physics. Any questions? The mathematics seems to be extremely simple, but when you apply it to cases, it has very deep consequences. So in particular, let us now discuss what is discussed in the book. It's called the rocket movement. When a rocket moves, it keeps on throwing particles backwards. Because of momentum conservation, if a rocket with the fuel is moving, if it throws some of its fuel backwards, it will be accelerated. And that's what we are going to discuss. And the only physics principle involved is the conservation of momentum. So we think of a rocket with a mass of m, with a velocity of v. It keeps on throwing material backwards. So later on, after a dt interval of time, it has a mass which we shall call m plus dm. dm is a negative quantity. It has thrown away some mass, and there's a minus dm here. In other words, after a small time, the rocket becomes lighter. It becomes m plus dm, where dm is negative. And that minus dm is thrown, it's still moving, but it's not moving with the same velocity as the big rocket. Let this velocity be v plus dv. And let's write this velocity as u. So originally it's this system, finally it's this system. What is the initial momentum? Is mv. What is the final momentum? Conservation. There are no additional forces. We are thinking of the rocket already out of the atmosphere. So there is no more resistance, and let us forget about the gravity for the time being. So the total momentum of the rocket is this, and that should be equal to the total momentum here. So it's equal to minus dm times v plus v plus dv times m plus dm. That's the conservation of momentum. Okay, let's calculate. This is equal to minus v dm plus mv plus m dv plus v dm plus dv dm. So this becomes the 4 terms. Now this mv term cancels this mv term. This vdm cancels this vdm. Pardon? Just a second, something is wrong. Sorry. This is u, sorry. This is not v, this is u. Now what is u? U is equal to the velocity of the rocket minus a relative velocity. The rocket throws the fuel backwards with a certain velocity, and that velocity is so this becomes minus dm times v plus dv minus v relative plus vm plus mdv plus vdm plus dvdm. This is equal to mv. Now first we cancel all these 2 terms. dvdm is quadratic. When you have 2 d's, it's infinitesimal compared to the rest of the terms. So this term, when you go to infinitesimal intervals, goes to 0. We have minus VDM and this plus VDM, so that cancels this. dm dV is 0 for the same reason. So therefore what we have is 0 equal to dm times V relative plus m dV. So we have dV is equal to minus V relative times dm over m. This is a very important formula. If I integrate both sides, I get the V, say, final minus V initial. It's a rocket which now is no longer, we're no longer considering an infinitesimal time. We consider a long time. So the final velocity times the initial velocity is the integral of the left side is equal to minus V relative times integral dm over m. Does anybody know what is the integral of dm over m? Integral dx over x is equal to log x from a to b is equal to dx from a to b. So that is, this log is the natural logarithm. It's the logarithm with respect to the base of e. E is 2.717, etc., etc. E is the most important quantity. E is equal to 1 plus 1 plus 1/3 plus 1/4. Sorry. It's a 1 plus 1. Is equal to 2.718, etc. Does anybody know why, where does the quantity E first occur? In daily life, there's the concept of E already. Does anybody know what, how that comes up? It comes up in compound interest. You know, if you put your money into the bank, if there is a interest every year, say you put $100 and the interest rate is 10% per year, so therefore after 1 year you get $10. But the bank may say that we compound the interest twice a year. Then if you compound the interest twice a year, then the half-year interest is 5%. So after 6 months, your money becomes 1.05. After another half, you get 1.05 times 1.05. Because every half year you multiply by 1.05. And you can see that this is larger than 1.1. So the bank says, okay, now we are going to compound the interest quarterly. Then it becomes 1.25, 1.025 raised to the fourth power. This is a 1.5 raised to the second power. Okay, the bank can compound the interest every second. Then you get something where the power becomes very large, but the interest each time is small. When that goes to the limit of the, if it gives you interest in every microsecond, the number E would come. This is a very important quantity. But anyway, if you have not learned this, you will be learning it in mathematics very soon. And with that as the base, you get this formula. So this becomes V times log of M final initial is equal to minus V relative. It's a log of M final divided by M initial. M final is of course smaller than M initial, so this minus sign becomes log of M initial divided by M final. V final minus V initial is equal. It says that the increase of the velocity is equal to the velocity of throwing back V relative times the logarithm of the initial mass divided by the final mass. This is the most important formula for all the people who do rocketeering. Now you first see the logarithm is a very small, it's a very slowly varying thing. You know that the log of the log to the base of 10, that's what we are more familiar. Log of 10 to the base of 10 is 1. Log of 100 to the base of 10 is only 2. Log of 1,000 to the base of 10 is only 3. So the quantity M may increase very fast, but its log increases very slowly. That's why the rocket, you have tons and tons of original rocket, and yet you have only a very small payload. Because if you want the V to be large, this V final to be large, you want this ratio to be very large. And yet this ratio, even if you make a very large one, the logarithm of it is not very large. So what you need to do is first you need to increase V relative. Now how is V relative done? V relative consists of, you have tubes. You see those rockets with tubes. The tubes has material inside which you heat up, and because it's very hot, it throws a jet, and so therefore you usually have 4 jets, and therefore it pushes according to what we just said, it pushes it up with an increase which is proportional to V relative. Therefore a key point is you want to have as high a V relative as possible. Now what is the V relative? You heat it up at a very high temperature. So you want a material inside of it which at a given temperature you want it to be as fast as possible. Now later on we are going to learn that at a temperature a gas has a velocity for a given, in thermodynamics we are going to learn that at a temperature T, the temperature is related to the velocity of the particles inside by this formula. This is due to Maxwell, where K is a constant. So if you can heat up at a given temperature the material you choose so as to produce the maximum V, that V is the V relative, should be the one with the lightest mass. What is the lightest mass? Is hydrogen. So therefore you burn hydrogen. If you burn helium or not burn. You heat up. If you heat up oxygen, for example, that's not as good because the velocity is much less. So that's why what you do is you have a liquid hydrogen in there. You heat it up, and then the hydrogen becomes a jet going downwards, and it pushes the rocket up. The other thing is that if you want to have a high velocity, if you have a fixed initial mass, you need a small final mass. If this is Mi is fixed, if Mf is very small, this becomes large. So that means that if you have a very small payload, then you can have high velocity. Or vice versa. If you want to have high velocity, you better have a very small payload. This also says that if you have a rocket, the rocket consists of fuel and machinery. And for a big rocket, the machinery is very heavy. So that now explains why you needed 2 or 3 stages. Because we can ask the question, why multiple stages? It's not as easy to understand this through this formula, but you can think of it as follows. You have a big rocket which is moving. You have a finer payload, Mi. If in the middle it does not discard part of the machinery, then the final mass cannot be very small. These rockets are huge. It has fuel, which you try to put in as much as possible. But nevertheless, the rocket machine has a heavy weight. You don't want that to be in the final mass, because you want the final mass to be as small as possible. That's the reason why you discard it. You first get it up, and then you throw away the heavy. The rocket has 2 parts. One has a heavy machinery, one has a light machinery. You throw away the heavy machinery. If you can throw it away several times, that's better. So that in the end, you only have the absolute minimum necessary payload and no longer loaded down with any machinery. And that's why it's multiple stages. Okay, any questions? Section 9.9-8, external force due to internal mechanisms. Let us look at the car. If here is a road and we have a car going here, the car has some complicated internal mechanism. It burns the gasoline and it transmits that force, that energy, into the wheels or into the axle, and then the wheels turn. So now let's look at this car as a system. What are the forces on the car? Well, first there's gravitation, but the road has a reaction, so that usually balances It has to balance, otherwise the car would go up and down. So let us assume it's going on a smooth surface, so there's no force up or down. So the mg is exactly balanced by the normal reaction. But its wheel is turning, so it's going this way. So its wheel is turning this way. And therefore the wheel pushes the ground backwards. So the ground pushes, according to Newton's third law, the ground pushes the wheels forward. So if we look at the force not exerted by the car, but the force on the car, then in the front wheel there's this force, in the back wheel there's this force. So there are the following forces: gravity, which is balanced by the normal reaction, and then beyond that there are only the forces on the four wheels. So the total external force is equal to the sum of these four forces on the four wheels, and that's what accelerates the car. So you see, in this case, it's the source of the force is external, is internal. That source causes an external force. But if we calculate the Newton's law, we don't ask what's going on inside. We need only ask the total external force. So if you know the external force on the four wheels, you know the acceleration of the car. Is that clear? Okay, let's do an exercise, example. 10E. 10E says there's a skating rink with two people. Skating rink means there's no friction. And the two people, one is heavier, one is 40 kilograms, the other is 65 kilograms. And they hold a bar. Remember, there's no friction on the two persons. So, and they are, both of them are pulling on the rod. So they will be approaching each other. This man is pulled this way by a force T, and this man is pulled by the same force but going the other way. So we have M1 R1 double dot is equal to T, and is equal to M2 R2 double dot. The R1 is this way, R2 is this way. So we can integrate this. So we get M1 R1 dot is equal to M2 R2 dot plus a constant. But the constant is, we assume that the two people at t equal to 0 are both not moving. So in that case, at that time, this is 0, this is 0, so this is 0. So we don't have this term. Now we integrate it once more. Let us take R1 to be equal to 0 when they were starting. We take R2 to be equal to 0 That it depends on how you choose R1, R2. So we choose R1 equal to R2 equal to 0 at t equal to 0. Therefore, we get M1 R1 equal to M2 R2. So that means the distance covered by each person is inversely proportional to their masses. So the heavy person will travel less distance. So when the two meet, the heavier person would have traveled a smaller distance. This is of course intuitively clear because the lighter person with the same force clearly moves faster. He's accelerated faster. So this is a conclusion which is completely intuitively correct. As I said once before, if you get a conclusion which is contradictory to your intuition, that is in fact a good thing, because either you have made a mistake or you have some fundamental misconcepts, and that's when you really learn something. Let's try 39p. 39p says there is something that explodes into three pieces. One piece with mass m, another piece with also mass m, a third piece with mass 3m. And the first piece and the second piece go at the same velocity but perpendicular to each other. The question is, what is the velocity of this third piece? An explosion means that it's an internal force. Nobody externally touched it. So the original momentum is zero. After explosion, therefore, the total momentum has to be zero. The total P must be zero according to the conservation of momentum. So it's trivial. If this is the, it's obvious that it's symmetrical, so it has to go at 45 degrees. And so therefore, V3 times cosine of 45 degrees has to exactly balance mv. M3m is the mass of this times the velocity of the third particle has to be equal to mv. So therefore, V3 is equal to V divided by 3 cosine of 45 degrees. Cosine of 45 degrees is 1 over square root of 2. So it's equal to 3 is equal to square root of 2 divided by 3 times 3. Okay, let's do another one. This one talks about the two bulges. Bulge 就是是不是叫拖船？就是一个大船里头可以通常是运货的。所以有两个 bulge， 一个走得快，一个走得慢。这两个 barge 它的速度差了10个kilometer， 它的 velocity difference 是10个 kilometers per hour。所以那个快的船就要赶上那个慢的船。比如说是，假如说是这个是快的，这个是慢的，这是快船，这是慢船。他在这个时候，把这个一个船里头的，比如说把这个快船上的这个煤产到这个慢的船上，他 assume 没有什么任何的 friction， 那要发生什么事情呢？他这个产的这个速度是 transfer of coal at 1000个 kilograms per minute。是这个 presumer 是一个机器，这个机器把这上面的运到这上面去。那这上面这个，这样好了，我们把这从慢的往快的运。这个慢的到快的运的时候，在慢的那个地方，它那个走的速度没有快的那个速度大，所以假如他要是他现在 assume 这两个barge 是稳步前进，就是 no change of velocity。那假如这个慢的这个要是把它这个煤放到这个快的这么放过去的，那就要发生什么问题呢？那个快的就要走慢了，因为它原来的这个是走的比较慢，你忽然晃到一个走得快的东西来的，当然它要把那个船向后拉一点，所以它这个所以你得做什么事情呢？得要把这个慢的这个船里的这些煤啊，得要加速到使得它跟那个快的一样快，然后把它transfer过去。所以呢，它要是 transfer of coal of accelerated coal， 这个 acceleration 是什么呢？amount of momentum transferred, of momentum added to the transferred coal。 它需要 transfer 这个 momentum transfer of accelerated coal， 这个 amount of momentum added to the coal 呢，很显然是1000个 kilogram per minute 乘上这个10个 kilogram per hour， 10个 kilometer per hour， 就是 mv， 不过这是 per unit per minute， 它要 transfer 这么多。遇到这种题目，你得先把那些不是 standard 的不是 standard unit 变成 standard unit。这它1000个，我看它是10个 kilogram， 10个 kilometers per hour， 这是1000个 kilograms per minute， 就是那所以我先把它变成1000个 kilogram per minute 是60 seconds， 因为我们都要变成 standard。 这是10个 kilogram， 是10个 kilometers， 那就是10的4次方的 meters。Divided by hour 是36 seconds， 3600 seconds， 所以这等于1000乘上10的4次方 divided by 3600 of divided by 3600 times 60， 乘上的 unit 是 kilogram per meter per second square。 这很好了，因为这是 Newton， 所以等于这么多 Newton。What it means 就是得要用这么多的 Newton 的 force， 把那个慢的船上的这个向前面 push， 把它 push 到那个快的船上去，才可以使得两个船都是继续的这个 velocity， 继续原来的 velocity。 这有没有 work 呢？没有 work。 为什么没有 work 呢？因为他把它要送到那边去，所以它是一个是一个 horizontal 的 force。这是讲一个车，这个车它这个 weight of car 是等于weight 是一个 force， 就是 gravitation 的 pull on it， 所以它的 mass 呢是等于divided by 9.78，它的 velocity 呢是等于113个 kilometers per hour。 它在一个 rough 的 surface 上走，它有个 resistance， 那 resistance 这个 force是等于83个 Newton， 这是题目所给的。这题目倒很容易了，因为第一样我们就可以算它的 mass， 算它的 acceleration，ma 是等于这个 force， 所以这 acceleration 就等于83，就等于 force divided by mass， 这都有点给了。等于，我知道这叫 weight 好了。不是。所以 force 是等于 F divided m。M 是等于 W divided by G， 他的题目问你 What is the velocity？ 因为它是 uniform acceleration， 所以它的 velocity 呢 velocity square 是到它停了是等于2a 等于 2a distance， 所以你就知道 distance。所以这 distance 是等于 v squared over 2a 等于 v squared over 2fg w， 这些都给了。 我们做56P。有一个 mass 是1500个 kilogram， 在一个时间30秒钟，它的velocity 是72 kilometers per hour。它这个 particle 这个 car 被 accelerated 了，在30秒钟，从 zero velocity 到了这个72个 kilometers per hour。它第一问你 ，What is the kinetic energy at the end of the 72 at the end of 30 seconds? Of course, the kinetic energy是等于1/2 mv squared。第二个问题是问你 average power。Average power is equal to the total energy done divided by the time duration. The total energy done is 1/2 mv squared divided by the time. The time is t. 第三个ask 是 What is the power at the end？ 它这个越 push 越快，它是一个 uniform， 它 assume 是一个 uniform 的 acceleration。那么它的 acceleration 是等于 final velocity divided by time。Uniform acceleration means the velocity is equal to vt。所以 the final velocity divided by time is equal to the acceleration. So what is the force? The force is equal to ma. So it's equal to mv over t. What is the power? You have a force. The power is equal to the force. The work done by the force. This is the final power. Instantaneous power. At the end. 就等于 force times the distance traveled per second. So it's equal to 4 times force times the velocity. So that's equal to mv over t times velocity. 这个题目的意思就是你看 this is twice this. The average velocity is 1/2 mv squared divided by t, while the instantaneous power at the end is mv squared over t. So this is twice that. Why? Does that correspond to your feeling? You are pushing something faster and faster, and you push it with a constant force. Originally, although the force is the same as the end, but it doesn't move. Originally it moves very slowly, so therefore you don't do much. The power is very small. Power is equal to the work done per second, and because it's not moving, so the work done is very small. In the end, the work done is large because for the same force, its distance is large. So therefore, that is twice is very easy to understand. Any questions? Okay. What we have learned today, first, the important thing is the center of mass. And it's important to recognize the center of mass is a geometrical quantity. Although we defined it algebraically, it's a geometrical quantity. It's independent of your choice of coordinates, although the definition involves the choice of coordinates. And that it's intrinsic in the sense that you can think of groups of particles. If you have a big body, it has groups of particles, and the total center of mass is in some sense equivalent to the center of mass, as if each one of them were concentrated in their respective center of mass. The other thing we learned is that there is a very important thing, is that the total momentum change summing over all particles is equal to the rate of total momentum change is equal to the total external force. So if something does not have any external force, like in an explosion, momentum is conserved. Now if you have two particles colliding with each other, if I have two say billiards colliding with each other, originally you have P1, P2. The momentum of the first one and the momentum of the second one as vectors. This is the total momentum. Afterwards, it may go this way. That has to be equal to P1 prime plus P2 prime. That's the conservation of momentum. Now in a billiard collision, it's called elastic. Elastic means that it does not lose energy. It's best if you first discuss an inelastic collision. If you have the two bodies which are soft, in fact, if you have two mud balls and make them collide, they will become one and stop. So this formula is still correct. In that case, you only have one, which is a zero. If you have two mud balls colliding with each other with the same speed but in opposite directions, and if they stick to each other, then the total momentum originally is P minus C. The final momentum is also zero. That's an inelastic collision. Why is it called inelastic? Because the total kinetic energy has become less. In fact, the original kinetic energy, the two of them are the same, but the final kinetic energy is zero. So that's called an inelastic collision. In a billiard ball, a billiard ball is almost perfectly elastic. That means energy is conserved. So if you have these two billiard balls, if they are not colliding head on, they would change direction. And of course they are still going opposite to each other. But the speed would not be changed, because if the speed will change, then the energy is not conserved. So in an elastic collision, you have P1 plus P2 equal to P1 prime plus P2 prime. You have 1/2 of m1 v1 squared plus 1/2 of m2 v2 squared is equal to 1/2 of m1 v1 prime squared plus 1/2 of m2 v2 prime squared. So that has both conservation with elastic collisions. Momentum is conserved. The vector momentum is conserved and the energy is conserved. With an inelastic collision, the momentum is still conserved, but the energy is lost. The kinetic energy is lost. What it does is that it becomes heat energy. If you also add the heat energy, then the energy is still conserved. But that is a topic that we shall discuss in thermodynamics. In elementary particle physics, what people do all the time is to make collisions. The first important realization that collisions are very important to study was an experiment done by Rutherford. At the beginning of the 20th century, people knew that there were electrons in atoms. People also knew that the electrons were very light, and therefore atoms must consist of other things which are much heavier than electrons. But what was the structure of an atom was unknown. So there were all kinds of models. One of them was the model of J.J. Thomson. He knew that the electrons were negatively charged. So since the total atom is neutral, so there must be some positively charged thing. So he thought, this was at the beginning of the 20th century, that the positively charged thing forms a big ball. It's a model. And the negatively charged electrons were embedded in this big mass, so that the total energy, the total charge is zero, and the total mass mostly is the mass of the positive charges. Some people call it the Putin model. Putin, a kind of dessert. But a revolution came when an experiment done by Rutherford and his student. What he did was he shoot an alpha particle into gold. So they know that the gold is very heavy, so it's something which is very heavy. And an alpha particle comes in, and he studies how the alpha particle is scattered by this. Now that scattering is of course conserves momentum and conserves energy. That were already well established. But the question was there possibility of very large scattering? And Rutherford, they found this scattering, the probability of scattering at various angles, theta. If it goes this way, the angle is called scattering angle, theta. Rutherford looked at the distribution relative to theta and realized that there must be a heavy central object in the center of gold atom, which is heavy and was able to deflect the alpha particle into this. And therefore there was the Rutherford model. That was the beginning of how one knew the structure of the atom. It consists of a heavy nucleus with electrons going around it, but these electrons are not studied at that time by this experiment. An alpha particle comes in. Alpha particle is much lighter than the gold nucleus, and because of Coulomb interaction, it gets reflected. It depends on, if it's almost hitting, it will get reflected very much. If it's at a distance, it will just be slightly deflected. And Rutherford, although Rutherford knew very little mathematics, he was very intelligent, and he figured out with the Coulomb interaction what the distribution should be, and it was in exact agreement with experiments. Therefore, the concept of the Rutherford atom was born, and that is still basically the understanding today, except we know that the Rutherford calculation was correct, not because his reasoning was correct. It's accidentally in quantum mechanics, later on, some 12 years later, people learned that the motion of the electron or motion of alpha particle in an atom should be governed by quantum mechanics and not by classical mechanics. But it just happens that the quantum mechanical reflection formula is exactly the same as the formula that he derived in classical mechanics. So, fortunately, physicists first learned from Rutherford through wrong reasoning, the correct model. And then people began to study more aspects of that model and found that the model is in general correct, but the mechanics was wrong. And finally, in 1925 to 1927, quantum mechanics was born. And that is still our understanding today of the fundamental structure of atoms and of molecules and so on and so forth. So after that, we know that if you want to study these structures of minute things, you need to do collisions. You need to do scattering, elastic scattering and inelastic scattering. Now, the asymptotic freedom Nobel Prize, which was just announced last week, was about some scattering, about some elastic and inelastic scattering. And the theory of that became clarified with the work of these three people. And that's why they got the Nobel Prize this year. Okay, so we'll meet again next Monday, and we'll go into rotational motion.